You already know how basic single-loop circuits work from your earlier studies, but real-world electronics, from the motherboard in your computer to the sensor network in a modern car, rely on complex branching paths and dynamic components. This unit gives you the mathematical and logical tools to untangle those networks. We will use two fundamental rules of the universe, the conservation of charge and the conservation of energy, to unlock the behavior of absolutely any circuit. An A-star candidate does not memorize circuit behavior. They systematically deduce it.
Everything starts with Kirchhoff's two laws. The first law tells us that charge cannot be created or destroyed at a junction. Whatever total current flows in must exactly equal the total current flowing out. The second law tells us that energy is conserved around any closed loop. The total electromotive force put into the loop exactly matches the potential difference dropped across its components. These are your master keys. You will use them to build simultaneous equations and solve for unknown currents and voltages in highly complex networks. Next, we develop mathematical shortcuts. Instead of applying Kirchhoff's laws to every single individual component, you will learn to collapse complex webs of resistors into a single equivalent resistance. You will derive the combination rules for series and parallel circuits from first principles, and then use them to simplify massive circuits in seconds. This is the silent workhorse behind almost every Paper 2 electricity question. If you can simplify the circuit, you can solve the problem. Then we meet the potential divider. This is a brilliant practical circuit that splits a source voltage to provide a specific variable output. You will use this exact formula to calculate that output voltage. More importantly, you will replace fixed resistors with environmental sensors, like thermistors and light-dependent resistors. This allows you to design control circuits that respond dynamically to their surroundings. A thermostat, an automatic street lamp, a volume dial, all of them rely on this one elegant toolkit.
Finally, we bridge the gap between theoretical physics and practical engineering. Real batteries are not perfect. They have internal resistance. They steal some of their own voltage, known as lost volts, before it ever reaches your external circuit. You will plot terminal potential difference against current. Because the lost volts increase as the current increases, the graph slopes downwards. The y-intercept reveals the true electromotive force of the cell, and the negative gradient gives you the internal resistance. Mapping this exact graph is a massive part of your Paper 3 practical exams. In summary, this unit transforms you from a student who can calculate a single loop into a physicist who can untangle any electrical network. You will master the conservation laws, simplify complex grids, design sensor circuits, and account for the imperfections of real power supplies. You are now ready to begin DC circuits.